In this short video, I'm going to compute partial derivatives for a variety of examples. Let's start with a reminder about partial derivatives. If we have a function f which depends on both x and y, then the partial derivative with respect to x is just the derivative of f treating y as a constant. And below this we can see the notation that we're going to use. Rather than the standard df by dx, we're going to think of this partial derivative as delta f by delta x. Similarly, if we have a function f which depends on x and y, then the partial derivative with respect to y is just the derivative of f treating x as a constant. So for both of these partial derivatives, the basic idea is that we want to understand how our function f changes with just one of its arguments. And in order to capture that, we're going to treat the other variable as a constant. In our first example, we're going to compute the two partial derivatives of the function f equals 16x to the 0.75 minus y. So we're going to start with the partial derivative of our f function with respect to x. Before I do any computation, I always like to take a look at my function and highlight any terms that have an x in them, because I know when I'm taking this partial derivative with respect to x, I'm treating that y value as a constant. So any terms that just have y in them are going to drop out as if they were a number. So I've highlighted my first term in my function f because that's the only term that has an x in it. And we see that this partial derivative is going to be exceedingly simple to compute. So we want to understand how f, which depends on both x and y, changes as x changes, holding y constant. We observe that x lives only in the first term and y lives only in the second term. So to differentiate this function with respect to x, we just have to follow that power rule or exponent rule that you probably learned in your Calc 1 classes. So we're going to bring the power down, the 0.75. We're going to multiply it by 16x, and we're going to reduce the power on x by 1. So I'm going to write this all the way out. We have 0.75 minus 1. Now let's simplify this thing. So the partial derivative of f with respect to x is equal to 0.75 times 16, which is 12. And then we have x to the negative 0.25. Now we're going to do the same thing, except we're going to compute the partial derivative of our function f with respect to y. I'm going to erase my highlighting here. We're going to do the same sort of exercise. We know now that we want to understand how f changes with y. So I'm going to highlight any terms in my function that contain y. There's only one term that contains a y. And then we're going to differentiate that term with respect to y. So here all we're doing is we're differentiating negative y. If it helps you, you can imagine that this y is raised to a 1 power, in which case we can follow the same rule where this partial derivative is equal to negative, bringing down the power 1, y to the 1 minus 1. And if we simplify this, y to the 1 minus 1 is y to the 0, and anything raised to the 0 power is equal to 1, so the partial derivative of f with respect to y is equal to negative 1. In our second example, we're going to compute the two partial derivatives of the function f equals 20x times y minus x. We'll start with the partial derivative of f with respect to x. Just like last time, let's highlight the terms that have x's in them. So the first term is 20xy, and the second term is x. So both of our terms have x. That's going to make our differentiation process a little bit more difficult. Also, as we look at this function, I want you to notice that unlike example 1, where x and y were in separate terms, here x and y coexist in term 1. So we're really going to have to do a little bit of mental work to successfully find the two partial derivatives. So when we want to compute the partial derivative of f with respect to x, I want you to have this little mantra that you say as you compute these. Y is being held constant. So we're going to treat y just as we treat the 20 when we see this function. So the first thing I like to do when I see a term that has both x and y in it is I want to write down all of the constants so I don't forget any of them. So if I'm differentiating with respect to x, the constants are the 20 and the y in the first term. So I know that this partial derivative is going to start out with a 20 and a y. And now I have to think about what is the derivative of x, right? So we really have this clump of constants, 20y multiplied by x. If you remember from your calculus classes, any constant term times x, the derivative of that is just going to be the constant. And you can prove it to yourself if you want to. You can think of x as being raised to the 1 power and take the derivative. I'm not going to do that here. I'm just going to deduce that the derivative of 20xy with respect to x is just the constant terms, which are 20y. We're not done though, because we also have to take the derivative of our second term, negative x. We know this one. The derivative of negative x is just negative 1. So we found the partial with respect to x. Now let's find the partial derivative of f with respect to y. I'm going to erase my highlighting here and highlight again. Here we're now going to, instead of focusing on x, we're going to identify terms that have y in them, and y only appears in our second term. So when we take this partial derivative with respect to y, we notice that x and y coexist in the first term, so we have to use our mind to sort of remind ourselves that this partial derivative with respect to y is assuming that x is held constant. So 20 is a constant and x is a constant, and those two terms are both multiplied by y to the 1 power. So when we differentiate with respect to y, we're just left with the constants, which are 20x. In this third example, we're going to compute the partial derivatives of the function f equals x to the 0.7, y to the 0.3. So I want you to notice, again, we have x and y interacting in a single term. And in this case, it's more complicated than example 2 because they're raised to fractional powers. We'll start with the partial derivative of f with respect to x. Keep in mind, as we take this partial derivative, y is being held constant. So we're differentiating with respect to x. We're going to follow standard derivative rules. We're going to bring down the power, 0.7, and we're going to multiply that by x to the 0.7 minus 1. I'm reducing the power by 1. And then I need to make sure to multiply by y to the 0.3 because y to the 0.3 is just some constant that's attached to the x term. To finish this off, we can simplify it a little bit. I'm going to deal with the powers of x. So I end up with 0.7 x to the 0.7 minus 1, which is negative 0.3 times y to the 0.3. Now let's do the same thing, except we're going to differentiate with respect to y. So our terms are commingling. X and y are in the same term. We want to differentiate with respect to y, which means we're going to treat x as a constant. So following the rules of differentiation, I'm going to bring down the power on y. So I have 0.3. And then I'm going to write that constant term, x to the 0.7. I write it down because it's attached to the y, which I'm differentiating with respect to. And now I have to deal with the rest of that derivative. For y, I have y to the 0.3 minus 1. And then finally, we can simplify. We end up with 0.3, x to the 0.7, y to the 0.3 minus 1, which is negative 0.7. This is the most common kind of derivative that we will be doing in our class this semester. So if you're going to focus on anything, I want you to be focusing on this kind of derivative where we have x and y multiplied together and raised to powers. In this fourth example, we're going to compute the two partial derivatives of the function f equals 60x minus 2x squared minus 2xy. So this is a little different from some of our previous examples because it has three terms. Some of the terms have just x, some of them have x and y, and also we have powers that are greater than 1. We'll start with the partial derivative with respect to x. And I think in this case it's nice to do a little bit of highlighting. So we're going to highlight all the terms that have x in them. So the first term has an x, the second term has an x, and the third term has an x as well. That means that when we take this partial derivative with respect to f, our solution should have three terms in it. So the derivative of 60x with respect to x is 60. And the derivative of negative 2x squared, we're going to follow our rules. So I'm going to throw this negative down so I don't forget it. I'm going to bring down the power of 2, and I'm going to multiply it by 2x to the 2 minus 1. And then I have to deal with my third term, which is minus 2x squared. I remind myself that as I take this partial derivative, y is a constant. So I have two constant terms, 2y, multiplied by my variable of interest, x, and the derivative of that will just be negative 2y. We can simplify this. We have 60 minus 2 times 2 is minus 4. X to the 2 minus 1 is just x minus 2y. Now we can move on and we can compute the partial derivative of f with respect to y. Erasing my highlighting, let's identify which terms have a y in them. First term doesn't, second term doesn't, but the third term does have a y. So we're going to focus on that as we take this partial derivative. So we're asking ourselves, how does f change with y? Well, it doesn't change through 60x. It doesn't change through the negative 2x squared term because neither of those have a y in them. It only is changing through this negative 2xy, the final term. So every 1 unit increase in y should cause f to decrease by negative 2x. Following the rules of differentiation, we'll see that that's true. We have y multiplied by a constant term, negative 2x, and we know the derivative of that is just the constant. In our fifth and final example, we're going to compute the two partial derivatives of the function f, which equals parentheses y minus x times parentheses 270 minus 3xy. So this is actually a much more complicated derivative to compute, which is why I left it for the end. And the reason why it's much more complicated is because we're going to have to use the product rule, which I have noticed students just do not like. And the sort of intermingling of the product rule and partial derivatives can really throw people for a loop. So I'm just going to verbally remind you about the product rule. The product rule is for taking derivatives of two functions multiplied together. So here we can imagine that y minus x is a function, and it is multiplied by the function 270 minus 3xy. And in order to take this derivative, we need to understand how the first function changes and how that affects the value of the derivative. And we also have to account for how the second function changes and how that affects the value of the derivative. As a result, the product rule tells us you should differentiate the first term and multiply it by the second term, and then add the opposite case, where the opposite case is you leave the first term alone and you multiply it by the derivative of the second term. Let's start by computing the partial derivative of f with respect to x. If you follow the rules of the product rule, it is simple. Don't let it overwhelm you. So the product rule says take the derivative of the first term, and here we have to add a little bit, take the derivative with respect to x. So the derivative of y minus x with respect to x is just negative 1. So I'm going to write that down. And then I'm going to multiply it by the second term, 270 minus 3xy. So that's half of the product rule. The other half says, well, you're going to add the derivative of the second term multiplied by the first term. So we have to take the derivative of our second term. Just so we're clear, when I say second term, I'm talking about this right here. So we need to find the partial derivative of that term with respect to x. The 270 drops out, it doesn't have an x in it. The minus 3xy, y is treated as a constant, so this derivative is just negative 3y. So what do we do with this derivative of the second term? We have to multiply it by the first term, y minus x. So notice that there are two terms to a derivative that comes from a two terms multiplied together function. We have the derivative of the first term here times the second term left alone, plus the derivative of the second term here times the first term left alone. Let's simplify this thing. So I'm going to distribute my negative in. I have minus 270 plus 3xy minus 3y times y, which is minus 3y squared. And then I have a minus times a minus, so plus 3xy. And then I can do a little bit of term combination because I have two 3xy terms. So I have 6xy minus 3y squared minus 270. And that's the partial derivative with respect to x. Now let's compute the partial derivative with respect to y. We're still going to have to use the product rule, but we've seen it once, so it'll seem a little bit easier the second time around. So we're treating x as a constant and we're differentiating with respect to y. We identify that both terms that are multiplied together have y in them, so we're going to have to use the product rule. So we're going to start by taking the derivative of the first term with respect to y. Well, the derivative of y minus x with respect to y is just 1. I don't technically have to write this one, but I'm going to for the sake of clarity. So I'm going to take that derivative, 1, I'm going to multiply it by the second term, 270 minus 3xy. Now I have to do the opposite case. I'm going to focus on that second term, the 270 minus 3xy, and I'm going to differentiate it with respect to y. So I'm treating x as a constant. So what's the derivative of 270 minus 3xy with respect to y? The 270 drops out. Y is just multiplied by the constant negative 3x, so we're just left with that constant, negative 3x. And then we take that derivative of the second term and we multiply it by the first term, y minus x. So again, we can see the parts of the product rule. We took the derivative of the first term, we multiplied it by the second term, and then we added the derivative of the second term multiplied by the first term. To finish this off, let's simplify. We have 270 minus 3xy, and then I have minus 3x times y, so minus 3xy. And then minus 3x times minus x is plus 3x squared. Just like last time, we do have two terms that we can combine because we have two 3xy terms. If we combine those, we get the final form of our partial derivative is 270 minus 6xy plus 3x squared.